Okay, so now we're going to continue along in the notes, and we're going to see if we can develop some other rules and other things for us to work with now that we have the power rule in our pocket. So we're going to do, I think, just one more, maybe two more, but I believe it's just one more formal definition of calculus, formal definition of the derivative, to figure out our next rule. So here we go. What we're going to do is work with a function that looks like this. Now you'll notice how this one looks different. The previous problems were just something like f of x equals x squared or x cubed, but now we have all this adding in, and the rule would hold if it was subtraction. I just put it all adding to make the formal definition a little easier to work with. So here we go. Let's use the formal definition of the derivative. And if you need a quick reminder, that was just the slope formula, where we said it was the limit as h approaches 0 of f of x plus h minus f of x, all divided by h after you simplify the denominator. So let's get our f of x plus h. So for this formula, for this function, when I substitute in x plus h, we would have x plus h quantity squared plus 3 times x plus h plus 1. So now let's do a little bit of distribution, a little bit of combining like terms, and see what we get. So this first one, when we distribute that all through and we do our expand it, that's going to end up being x squared plus 2xh plus h squared. Distributing this 3 through will give us 3x plus 3h plus 1. And I see no like terms to combine, so we'll just leave it like that. So then our second part of our formal definition just needs f of x. So therefore that would be x squared plus 3x plus 1. And to keep with the color coding I was using before, this will be the first part of our formal definition. This will be the second part of our formal definition for the numerator. So let's go ahead and fill it in. And I'll highlight it here too if you want to see. So there's the first part. And there's the second part. So let's go ahead and fill that in. So we're going to have the limit as h approaches 0 of x squared plus 2xh plus h squared plus 3x plus 3h plus 1, that's the whole first part, minus the second part, which was just the original function. You could see it's right there. So we'll go ahead and fill it in. So that's x squared plus 3x plus 1, all divided by h. And this is the first problem where you can see these parentheses are actually really going to be important, because it's telling me I need to distribute that negative sign to each of the terms. So now when I do that, the first set of parentheses is not so important. It didn't really matter. So we can drop those. So it's just going to give us x squared plus 2xh plus h squared plus 3x plus 3h plus 1. But now, so when we distribute that, we're going to get a little more interesting stuff. We're going to get negative x squared minus 3x minus 1, all divided by h. And just like every other problem before, we're going to look for things that subtract to 0. We're going to combine our like terms. So here I got x squared and x squared. Let's see what else. Here I have a negative 3x. Oh, here I have a positive 3x, so those subtract to 0. And here I have a negative 1. Here I have a positive 1. Fantastic. Okay, so now let's go ahead and see what we're left with. The limit as h approaches 0 of 2xh plus h squared plus 3h all over h. And you'll notice, just like before, every term that we have left in here all has an h in it. And that's awesome, because now we can factor out the h like we've done in the past. Factor the h out of the numerator. So it's going to give us 2x plus h plus 3, all divided by h. And we can, those divide to 1, so we can simplify that. And now I'm able to substitute in 0 for h, because remember, that's our goal, is just to get the equation simplified, to get this formula simplified to some point where we can now substitute in 0 and get an answer. So therefore, this is going to be 2x plus 0 plus 3, or aka 2x plus 3. So let's see, can we come up with a rule? Can we make a rule out of this? Well, if our original function was x squared plus 3x plus 1, and we use the power rule that we had developed in the previous problems, does this fit? Well, if you notice, the power rule for x squared, the answer was just 2x. And the power rule for x was just 1, but since we had 1 and it was multiplying by 3, we'd end up with 3. So if you kind of think of it like that, the derivative of x was 1, and then the whole thing was being multiplied by 3, so 3 times 1 makes 3. So the power rule, oh, and then the derivative of a constant was 0, which came up true here. So hopefully the rule we can come up with now is, the rule is called the sum and, that is the world's worst ampersand, there we go, sum and difference rule. And what does that rule say? Well, it says when you have things that are sums and differences, each, and the mathematical expression for that is called terms, so each term is done as a separate integral, or as a separate derivative. Or you could think of it as it's done as its own problem. However you want to phrase it. I'll put it this way. I'll say each term is done as its own problem. So you just look at it as if it was 3 separate derivatives. So if you go back up here and say, okay, how would I do the derivative of x squared? Well, the power rule says bring the 2 out to the front and subtract 1 from my exponent. Perfect. Okay, how would I do the derivative of 3x? Well, bring this out to the front. So that'd be 3 times 1 times x to the 0. And we all know anything to the 0 is 1. And so you can see it's falling out. There's one term, there's the next term, and then the last one would be y equals 1. So how do you do the derivative of that? How do you do the derivative of that? Well, the derivative of a constant, well, we can look at it in 2 different ways. We can say that's x to the 0, so the 0 come out to the front, making it 1 times 0, x to the negative 1. But hey, we all know 0 times anything makes 0, so there you go. There's your derivative. And then the other way you can look at it is think of it just like from the good old-fashioned slope. What would the graph of y equals 1 look like? Well, that would be something like this, right? And what's the slope of a horizontal line? 0. So we can see it both graphically or, and we won't actually graph it every single time, but you could think of it that way in your head and see that the slope would be 0. So nonetheless, so there we go. So now the notation that we would use to describe this rule might look something like this. What we're going to say is we want to do the derivative of lots of like individual little functions that are separated by addition. Like, so here this would be x squared, that would be x. And what this rule is saying is you can do them individually. We'd say do the derivative of f of x, then take the answer of that and add it to the derivative of g of x. So that would be kind of your notation for the sum and difference rule. Okay. Now we could continue to go through and do some algebra gymnastics and go through all of this wonderful stuff that I'm sure you all are enjoying thoroughly and are going to look up video after video of just so you can practice and have a lot of fun at home and do this on your weekends. Or I could give you a list of rules and you can agree that we don't need to prove them all to you. You can just accept them. So here you go. The first rule is called the constant multiple rule, which is one that we've already experienced, which just says if you have some constant multiplying your function, you do the derivative of your function like normal, take the answer of it, multiply by your constant. So for example, that would look something like this. If I had y equals 4 times x to the third, well, what it's saying is just kind of ignore the 4. Do the derivative of x cubed. We know the power rule that says the 3 comes out to the front and you subtract 1 from the exponent. So therefore now we're just going to say I have my derivative. I did my derivative of x cubed. Now take the answer of that, multiply by the constant that was out in the front. The constant out in the front was 4, so we're just going to multiply this by 4, which will give us 12x squared. Okay, that's the constant multiple rule. The next one's the sum or difference rule, and we just worked on that one. We just did that one, where it's saying if you have 2 things that are adding or 2 things that are subtracting, you can just break them up into individual derivatives and just take the answer and either add them or subtract them for whatever sign was there. Power rule, we also already did. The power rule. The power rule says you bring your exponent out to the front, subtract 1, and voila. When I say out to the front, note it's multiplying. Special cases, just note if you have a constant, the derivative is 0 for the reasons we already described. And if the other one that sometimes gets people is, remember, the derivative of x, really, that does have an exponent on it, right? When you say x, there's really an exponent of 1, and sometimes students just forget, so that 1 comes out to the front, making it x to the 0, and anything to the 0 is 1. So it ends up being 1 times 1, which is 1. So that's what they're just trying to remind you of there. That's equal sign did not want to cooperate. So that's what they're just trying to remind you of there. Okay? Exponential functions. Now, the exponential functions, they're showing you 2 rules here, but I'm going to argue that there's actually really only 1 rule, and it's this one here. What the rule says, to kind of point it out to you, is what it's saying is, do you see the base of your exponential function? It's some number. They used a. So the derivative of any exponential function is the natural log of the base times the original exponential you started with. So you'll see here. Let me give you an example. Let me give you an example here of something like 3 to the x. So therefore, the derivative of that would be, you start by saying, all right, the natural log of the base times the original exponential you started with. There's your derivative. Okay? Now, the reason that they are kind of arguing, the reason they're showing you 2 different rules here is because they're just simplifying for you. If I started with y equals e to the x, okay, the derivative would be the natural log of the base times the original exponential you started with. Well, what's the natural log of e? The natural log of e is 1, because the base of the natural log is e. That's e to the first, so when they simplify, because they're inverse operators, you end up with 1. So that's why the answer to this is just e to the x, because it's 1 times e to the x. So when you do the derivative of e to the x, or of an exponential function where the base is e, they're just already simplifying for you that the natural log of the base is 1. So you can remember it as 2 rules, you can remember it as 1 rule, however you want to look at it. Just that's what's going on there. Okay? Now, the last rule is the natural log rule. The natural log rule says the derivative of a natural log is 1 over the whatever's on the inside. So let me show you kind of, actually I can't show you a more advanced version yet because we haven't learned the chain rule, but once we get there we'll do a little more fun things with this. So for now it's going to seem kind of basic. It's just always 1 over the stuff. So let me give you a quick example where it's not 1 over, just so you can kind of see what's going on. So if I gave you something like this, 4 times the natural log of x, we're going to use 2 rules here simultaneously. What we're going to say is this is the constant multiple rule. So when you have a constant, you just kind of leave it alone, and you say, what's my derivative of natural log? Well, that would be 1 over x. So now, how do I multiply fractions? Well, I stick this over a 1, and now I multiply straight across. So I end up with 4 over x. So I've had students in the past get really upset because they say it's not 1 over. Well, it really is 1 over. It's just a lot of times we're just going to jump, or the book will jump straight to this answer. They won't show the in-between step because they're assuming you're going to be able to do that multiplication in your head. Okay, so those are 3 new rules. Let's practice them a little bit. So I've already kind of talked through these. So I would recommend pause the video on each one of these, give it a shot, and then unpause the video and see if you get the right answer. So this is an exponential function. So the derivative of an exponential function using that rule is the natural log of the base times the original function you started with the original exponential you started with. There you go. That one's done. Okay, the next one, a exponential function with base e. Well, that's actually not too bad, right? Because it's the natural log of the base times the original function you started with. But natural log of e is 1, so therefore we just end up with e to the x. And last but not least here, the derivative of natural log of x. Yep, you got it. That's 1 over x. Fantastic. Okay, and again, those will get harder. We just can't get harder until we learn some of the other rules. All right, so now moving along, let's find the derivative of this function. Well, right now we have a problem. We don't know how to do it. We've got all sorts of crazy derivatives in here. We have the sum and difference rule. We have all our rules, and then the whole thing is being squared. So right now, we only have one option. We've got to FOIL this through. We got to distribute all this through, and then we can see if we can do a derivative. Oops, but we can't do it yet. Okay, so when we distribute this through, this would be the equivalent of x squared plus 5x minus 2 times x squared plus 5x minus 2. I'm going to go ahead and pause the video, write all this out, and you can check to make sure you got the same answer as I did. Okay, so what I did, I went ahead and distributed everything through, and you can see I kind of color coded. So you can see the x squared times x squared. I followed through with the black here is following the x squared through as it distributes through. The red is distributing the 5x through, and then the blue is distributing the negative 2 through. And then you take each of those and add them all together, and you get f of x equals that. So now, could you do the derivative because when it looks like this? Well, yeah, since we don't have that squared on the outside anymore, we don't have to worry about, kind of how would we do a squared on the outside and then doing derivatives of stuff on the inside? I don't know. Well, I do know, and you will too in the next video. But for now, I don't know. So we have to distribute all that through. Now, when you look at these, this derivative doesn't look so bad. So again, you might want to pause the video, try it yourself, unpause the video. But here we go. Remember, when we have sum and differences, you just do them as individual little derivatives. So what's the derivative of x to the fourth? Well, that'd be 4x cubed, because you bring the exponent out to the front, and then subtract 1 from the exponent. All right, so the next one, how do I do the derivative of 10x cubed? Well, we ignore the 10, we do the derivative of x cubed, so that 3 would come out to the front. 3 times 10 makes 30x squared. Plus, bring the 2 out to the front, that would be 42x minus 20. Why 20? Well, remember, this has an exponent of 1, so the 1 comes out to the front, making it 20 times x to the 0. And as we know, anything to the 0 is always 1. Plus 4, derivative of a constant is 0, and the reason for that, remember, this is really times x to the 0, because anything to the 0 is 1. So when that 0 comes out to the front, it wipes out the whole thing. So there we go. So go ahead and you can go through your homework now and try to find problems that fit this pattern, fit these patterns, and you can work through them. And then when you're ready, you can go on to the next videos where we're going to learn about the chain rule and product rule. So any problems that just have sums and differences, that's fine. But if they start to have functions inside of functions, kind of like this problem here, where you had a whole bunch of stuff squared. So we kind of have like a function of x squared plus 5x minus 2 inside of a square. Those are product and product and chain rules. Put those off till the next video. So good luck, practice, 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 and we'll see you in the next video.